Let's jump into statistical discovery, the essence of today's discussion. Here is an example of tablet production. Okay, I'll just give you the process a little more, and then we'll take the data set and then I'll start analyzing it. This picture represents a process map of the production. It is a secondary drug process that involves milling of an active pharmaceutical ingredient API into a powder of uniform particle size. The milled material is then blended with other ingredients to bulk up and evenly distribute the API. That's the milling. This blended material is then compressed into tablets, which are finally coated to aid shelf life, taste, and other properties. That's the compression. At the end of the process, a dissolution test is performed. Dissolution is so critical in pharmacy, right? And if the average dissolution value of several tablets is less than 70% dissolved at 120 minutes, the tablet batch is rejected. This is a simple process. We'll take this example and let's go to the discovery mode. Okay, so we need to put now data to discovery. This is what you have a data and you want to discover something and make patterns and get into the action. So here is our journey from data to discovery. First, let's visualize the data, power of visualization. Then descriptive and inferential understanding, a bit more of multivariate analysis, and build a model. Post that, let's fine tune the model and run simulation, and then find the design space for optimal factor settings. Okay, so I may not take you through all those things in detail, but given due respect to time, we'll try to cover as much as possible. We'll also run multi-color simulations. We'll try to understand, explore design space. And if time permits, I'll also talk about DOE by taking a small mixture design experiment. So let me show that. So this is the end of PowerPoint presentation. Let me get back to the jump. Okay, so I hope everybody can see my screen. So this is the data set. You can see dissolution is here, screen size, mill time, blend time, spray rate, everything is part of it. So if you ask me where is this data, this looks like a simple Excel field, right? JMP is a desktop-based software. This data, if you want to use the same data as I go and explain you want to utilize the same data and explore, it is part of the example data set. So I'll show you, this is help, and you go there. There is a JMP documentation library. Books are part of JMP. You can go and explore the books also. Sample data library, you click it and it will take you to sample data library. Once you download JMP, JMP has 600 plus inbuilt data sets which you can leverage. So this is a tablet production data. You can see that this is the same data set I'm using. Or as another way to explore JMP is, you come here, there's a statistics index, statistics scripting index, sample data. If you click sample data, it's part of help menu. The data set is categorized based on the type of analysis as well. You can see here, or as the kind of data here. And it also has teaching scripts for teaching, examples for teaching, and most of you are the professors, and in fact everyone is a professor here. So teaching scripts, interactive teaching modules, so simulations, teaching demonstrations, everything part of it. So JMP will be helpful for researchers, scientists, and at the same time it helps the professors and students as well to learn better. Okay, so let's start with the visualization. Now this is the data set. If you have already downloaded JMP, you can also open it up, or else if I do a little fast, the video will be available. You can always go back and refer, and then you can also exercise this. So here is the data set. Okay, you can see dissolution. That's a small header graph here. So you click here and then say, okay, what is happening with my dissolution? I can see here it is 80.2 to 64.2. That's what the dissolution looks like. Mill time, screen size is 3, 5, 4. This is a small header graph, and you can see anything below 70 is been marked as red color. That means that's a rejected lot. It just gives you some basic information about the spread and categories of and also missing value. So JMP has a robust missing value treatment or else outlier treatment. I'll not get into that. Screening capabilities are also there. But what I would like to show is the JMP graphical visualization capabilities. JMP has powerful graphing capabilities, and one of them is Graph Builder. It gives you, it is under the graph menu, click Graph Builder. So let me make it big. So it gives you an opportunity to visualize and explore the data the way you want. Because that the discovery is very important. Given the same data set to two people, they might analyze in different ways. So that's the discovery word comes into the picture. So let's get into the graph. So this is what it gives you. This is the X, Y column, X rows, group by Y, group by X. You can see rapid overlay. So the first thing is I want to check the dissolution here. Okay, so I'll just drag and drop dissolution here. It gives me a scatter plot matrix. This is how it looks like. Hey, this is fine if these are all the controls available here within the jump. Now I want to see a box plot. Box plot is a powerful visual tool. I can click box plot here. Now I want a histogram here. I can click histogram here. I can see what is happening with my less than 70% as well. So this is, now I want a line graph here or a bar graph. I can click bar graph here. No, I want a little more box plot. That's fine. I'll stick onto the box plot here. And I want to see, let me put mill time, or else I want to see by screen size. I'll just take screen size and group it here. So you'll get the box plot based on the screen size here. I can easily make some observation here. You can see this, right? The screen size 5 has a lower dissolution. You can see here, this is the lower dissolution. And screen size 3 has a higher dissolution. Some kind of initial analysis. I got it, right? I'll start over here. I'll put the dissolution onto x-axis here. And I'll say I want to see based on mill time. I'll just drag and drop mill time here. It looks like there is a lower mill time is related to lower dissolution. I got some kind of observation. I'm making exploratory data analysis here. And then now that, let me take out this one here. I can put this way. So I can see, now I can add, I want to see blend time also. I can go ahead and then add blend time here. So it gives me blend time also. I'm just exploring. Mill time is below. Blend time also has a direct relationship, more or less. Not sure what is happening, but looks like it is also increasing. Let me check with the spray rate. So I'm not gone anywhere. I'm just dragging and dropping. Looks like spray time has a inverse kind of a relationship. It looks like decreasing. Let's keep that way. And I also want to see the coating viscosity. I'll drag and drop. See, all the 4 graphs I'm building here based on viscosity, spray rate, blend time, and mill time. And then if I want to see a little more on the regression, I'll go ahead and then click regression here. You can see coating viscosity has an increasing direct relationship. It has an inverse relationship. If I want to look at R square, I can see R square values here. And I can do many things here. Or you want to see a little more jitter here, you can go ahead and do jitter. At the same time, if you want to see based on the screen size, I can go ahead and then wrap it here. This is how. So now I haven't gone any other platform. I was able to do a little more on the what is happening. I can change it. I can play around with it. So I was able to explore the data visually. Very important thing. That's where it comes to the picture. Visualization of data is very critical. So I can add a data filter like this. I can go ahead and then I want to see by kind of what do you call it as? Let me check the compressor. Based on the compressor I want to add. I want to see compressor 1, what is the interaction? I want to see compressor 2, what is the interaction? If I want to save this, absolutely. You can go ahead and then save it as, export it as a PDF, HTML, interactive HTML, image. You can save it as a PowerPoint presentation or else a Word, whatever it is. Let me not show that. Now, most of the times I save it as an analysis within data set itself. So it's something else. Save the script to the data table and I'll say, go ahead. If I close this, you can see the data set. The script is saved here. I want to see what I exactly did. See, this is where I stopped here. So that's what I want to see a little more on the, I'll go the next visualization. I'll say, I want to do a little more on the heat map. So what I'll do is I'll drag and drop everything I want to see. Hey, let me not take the compressor here. Let me take this and I'll drag and drop here. So all those things gives me, let me take the dissolution here. I can get a little more on the color here and I'll click color heat map here and done. So somewhere I can understand all these 4 variables. Look at the red color. I'll change it the gradient here, reverse the gradient here. So I want to see the red colors or the low dissolution. So look at this. Anything above 70, below 70 has become red color here. So I can see with respect to blend time of 50, 15.5 to 16.4, there are a lot of red colors. With respect to mill time here, at the same time, there's a spray rate. So I made it 4-way analysis of the data. So this is visually understanding. So most of the problems can be identified and then solved using visual approaches in any of our experiments. So this gives you the capability to do. And if I start looking at it, I can drag and drop, show the control panel here, and I can come back here and say, okay, let me drag and drop each of the cases. So this is how you start visually exploring the data. Before getting into any of the sophisticated model and simulation, visually explore the data in the beginning. Is there any kind of interconnections between the X's and Y variables? I can also do a little more here. I'll go here and then traditional scatter plot 3D. I want to say explore these three variables. I'll go and then explore here. It can give me a little more on the 3D also. You can see here. So with respect to mill time, spray rate, and blend time, what is happening to my variables? That's what I can do here. So 3D scatter plot also. So let me save this also, whatever we did. Let me save the script to local data table. Yeah, scatter plot 3D, close. So another way is, the one visual modeling approach is in plotting the Y, the dissolution variable, with respect to X, side by side histogram, and looking at the dynamic linkage in JMP. I'll do here, it's go to analyze, distribution, and then select all the variables here, and then click Y. I want only histogram. I'll click OK here. So it gives me histograms of all the variables. And I'll go here and let me arrange into number of rows 6. Let's make it 6 here. So this is what it gives you. So now if I'm looking at this, the dissolution, and these are all the different variables and everything is. So if I'm looking at, if I want to explore, I'll select only the variables which dissolution is less than 70. So this is what the kind of a rejected lot for me, right? If anything less than 70 is not accepted, the tablet is not accepted from a dissolution standpoint. So in that case, there are some obvious clustering. You can see the clustering of defects seems to occur at high values of screen size. So if I select the high screen size 5 has a lot of defects. At the same time, with the low mill rate, you can see that. At the same way, high values of spray rate. This is the one best feature of JMP is called dynamic linkage. Even the data gets interlinked. You can see that I've selected less than 70. The data is also interlinked here. It says 12 records have been rejected, but there could be something which is closer to that also 69.7. We can explore that further. So you start exploring that. So probably in the next stage is, hey, I want to do a little bit of test of hypothesis or ANOVA. I want to check for the distribution, or else the normality check. I can go and then check summary statistics here. I can check whatever the mean, median, mode here, median, mode, and then I click here and it gives me a lot of options on the mean, median, mode. You can see that mean is around 72. And then say if I want to check whether it is normally distributed or not, I can come here and then check for normal quantity plot. So it gives me the Lilly force region here. So more or less, it is within the normal region. That's the Lilly force region. That means the dissolution is normally distributed, but I can also go ahead and fit a distribution. It's called normal distribution. I think when it comes to reliability in pharmacy, reliability of drug, you always try to fit a distribution, right? So it gives me these two tests. You can see that Shapiro-Wilk and as well as Anderson-Darling test. And both of them says it is normally distributed. You can go and then do a test of hypothesis or else an ANOVA. I haven't changed any platform here. I think I can go ahead here and fit Y by X, and I'll say dissolution here, and then screen size here, and then go automatically. It does a one-way ANOVA. So I can do little more here quickly. I can see that the 95% confidence levels are not matching here. You can see that there is no overlap. There is an overlap between the screen size 3 and 4, but not between 3 and 5. This is what that means. The test is significant. They're not overlapping. In these two cases, but overall the test, it is overlapping. Then I can also do a little more on the comparing means between kind of Turkish HSD. You can see that 3 and 5 are significant, 4 and 5 are significant, 3 and 4 are not significant. So that's how you can go ahead and then explore the data also. Or else if you are a quality person, you might be teaching quality by design. You can also do a little more on the go ahead and analyze here, quality and process, build a quality control charts. Just drag and drop here quality. You can see that. So the trend dissolution, you can see the trend of dissolution indicates that the process is sometimes likely to operate closer to the threshold of failure, because the threshold of failure is 70 here, and then it's closer to the threshold of failure. So as a scientist, as a researcher, it is necessary to shift the mean dissolution a little more higher value, and preferably shrink the variability around the mean to ensure all the future production of your tablets have a higher specification limit of 70, more than 70. One can also play around with a little more on the interactive process capability. I think this is something which you can always play around with. This is wonderful from JMP perspective. So just you keep playing around the target variable and then upper control limit. You can always do this. These are the things which are possible in JMP. Okay. So mean, sigma, you want to, so you can play around this. I'll close this. Let me save this also. File. Let me get back to, and then let me save this, whatever analysis I've done within control chart builder. Save the script, data table. I'll save this. Let me close this. And this also I showed you, save the script. So now we explored this little more from a one variable perspective, right? So now that I can also do a little more multivariate. Let me close this also. I'll come here, analyze multivariate. A lot of multivariate techniques are there, including the clustering, structural equation model. Probably you might not use it, but in future, partial least square, principal components, discriminant title. So I'll just check the multivariate analysis. I'll drag and drop everything, because initially we are not building any of the models here, but we are exploring the data here. So this gives you a little more on the correlation, and then little bit on the, this is what it is, the correlation matrix, and this gives you scatter plot matrix. You can see that. The one thing which I super like in JMP is, you can also build a fit align here, and then you can take out the data points here, and then you can see a little more of shaded eclipse here. So you can see that how variables are related to each other. Mill time with respect to dissolution, there is a positive correlation. Blend time with respect to dissolution, there is a positive correlation. You can also put a little more on a vertical histogram. So this gives you a little more interactive capability, or else you can see a little more on the color maps, on the correlation. So still I'm in the exploration of data, because the more you understand in the beginning, it will be a better discovery in future. So explore the data visually. So look at this, gives you a little more correlation. I can explore multiple things here, right? So principal components, even if I don't know anything, like, so for example, I don't know what is this scatter plot matrix is all about, I can go ahead and put a question mark here. It takes me to the internet, to the JMP website. It says that how to interpret the result, what it is all about. So that's also possible. So let me not take out little more time. It goes to that. So you have now explored the data from a multivariate perspective, right? So now what we can do is we can do multiple other aided tools in JMP are there to explore the data. So, but with the due respect to time, I'll get on the modeling, regression and modeling here. Let me save this also, multivariate. Save the script. I will share the script also, the data set with all of you. Post that. So this is what, so look at this. I just dragged and dropped a question mark on that. It went through the data set or the internet, and it gave me all the details about how to go about the interpret. Let me close this. So let me get back to modeling now. Okay, so very important things. With the solution proposed by all the visual exploratory methods is an improvement, but it is limited to pairwise comparisons, one factor, one outcome. So to define a safe production environment, I'll introduce another word you are all familiar with. It's called word QBD, quality by design. So one needs to know how a set of influential factors simultaneously affect the quality of the outcome. See, pharmaceutical production faces a lot of side conditions, right, from other industries, which they do not. So there are a lot of strict requirements with respect to transparency, quality and reliability, and authorities have to approve every change. So in an attempt to give little more flexibility to pharma companies and the freedom of decision, the concept of quality by design was developed. As part of QBD paradigm, Pharmaceutical quality is assured by understanding and controlling manufacturing and formulation of variables. These are the variables in the formulation we need to explore, understand, rather than a final inspection and screening a screening out non-conforming product. We need to understand by building a model to understand the influence more formally, and that becomes a base for further analysis, or you call it as optimization. So let's understand by building the model here. Okay, so what I do is I'll go here and then see analyze. Look at this predictive model. There are a lot of algorithms within JMP, be it support vector machine, naive Bayes, model comparison, bootstrap, partition, mixed model, generalized regression as well. So, but for the sake of it, probably generalized regression is highly used now. It's called penalized ridge regression, lasso, elastic net, pretty much used in pharmacy and pharmaceutical chemistry as well. But let's build a simple model, okay, and then understand and then simulate and optimize. Okay, I'll go here, analyze, fit model. Dissolution is my y variable. I'll take all other variables and I'll put it to x, okay, and I'll run them. This is, I'm formally establishing the relationship between x variables and my y variable here. Okay, so let's see what is happening. So it says that FX summary, that means screen size, mill size, blend time, spray rate, everything is important. Coating viscosity, but after coating viscosity, every other variable is not so significant. That means the p-value says that you can see the blue color line cut off as well. It gives me a lot other statistics which you can explore, and it gives me a prediction profiler also. I'll come to the prediction profiler. This is an important thing when it comes to predicting any of your variables here. So now that I realize that these are the 4 or 5 variables are important as an exploratory method, what I'll do is I'll select all these variables and I'll say I'll remove that and I'll rerun the model. I need not go back anywhere. I'll just say remove here. I'll select all these things. I'll say remove. JMP runs immediately, couple of seconds. It runs a model, it alters the model and say, okay, screen size, spray rate, blend time, mill time, and coating viscosity on the tablet is so critical for your dissolution. That's what it says. So now I got little information about this, right? So now the question is, I need to understand little more in depth, because a statistical model gave me only one variable it is. Now that I need to understand the interaction of these variables also. What I'll do is I will go and edit this. What I'll do is I'll take this and I'll add interaction. That means I'll go here and then select factorial to degree. What it does is screen size into mill time, screen size into blend time. These are all interaction variables. I can also do one level is I can also do a response surface. That means mill time into mill time. That is a quadratic expression. So that's called response surface. I will go here and I'll put a response surface here. So it add all those variables. So now I want to see the interaction as well. So I'm fine tuning my model using response surface and as well as interaction effect. I'll just say commit here. So JMP runs so quickly so that you can see that. Now the screen size, spray rate, mill time are important. Look at this, mill time multiplied by mill time is also equally important. Blend time is important. Look at the interaction, spray rate and coating viscosity combination at the same time, coating viscosity. So these are all important. What I'll do is I'll go ahead and then delete all these things. I'll remove those variables. I'm just on discovery mode. See, look at this. This has run. All of them are significant. And here I come. All the regression diagnostics are here. All those things. Very important. Now we'll come to prediction profiler. Okay. So profilers, before getting into the optimization, JMP has a lot of profilers, which I don't think so is there in any of your other softwares. I'll explain a little more profilers here. You can see the profiler, right? It's called prediction profiler. Very powerful. It's called, there are various profilers. One of them is prediction profiler. The prediction profiler in JMP displays the conditional relationship between y and a given predictor, given the level selected of other predictors. For example, I'll show you here. Okay, so if I fix the variable screen size as 3, I'll fix this, and I'll start moving mill time. What happens to my dissolution? You can visually see this, right? You can see visually what is happening to my dissolution. If I fix the mill time here and screen size at 3, if I vary the blend time, what happens to my dissolution here? You can see 75, it gives you a confidence level also. So that is where it helps. This is where the prediction profiler is so powerful. So look at this. If I keep 3 as my screen side, some of the things are the curvature in the mill sign. So you look at this. Initially, it increases the curvature and then automatically it decreases. Let me make it a little more big here. Okay. So you can see that. I have to play around this with that. Okay. So the curvature, you can see this, right? So the curvature is very interesting with respect to mill time here. It increases and then start decreasing it. At the same time, the interaction of spray rate and as well as I can say blend time and viscosity produce more interesting consequences. So you can see that if I keep the spray rate low, okay, at the low spray rate, the viscosity doesn't have any impact. Look at this, viscosity is almost flat. If I keep at spray rate, it doesn't have any impact on the dissolution. So visually enabling with the prediction profiler is so it explains you at a lower spray rate coating viscosity has no effect. Blend time has a direct relationship, spray rate has an inverse relationship. Look at the confidence interval also, 95% confidence level also it shows you. So this is what it gave me now. So the expected result is little more above it. Now that you look at a 75, 70 is our cutoff. Now that the next level is Monte Carlo simulation. Statistics is always dealing with variation. Okay, it is the reason for confidence. It is the reason for the confidence intervals. The subject of statistical tests and the rationale behind all modeling efforts. I use confidence interval and statistics. So it might be unlikely that the subject matter experts will follow the process settings with such detail as to know distribution of values, including this variation in the analysis. Makes the results much more representative of the actual population that will be produced from the guest. That's why you use little more simulation in your results. So one way to explore is the Monte Carlo simulation. So here is the input parameters. So JMP gives you, go ahead, first optimize the result. Okay, let me optimize the results. Desirability, I want to have maximum dissolution. Okay, so I'll go ahead and then click maximize, optimize, and I'll go ahead and then maximize my desirability. That means I want maximum dissolution. Give me the factor settings which can give me maximum dissolution. You can see here. So keep the screen size 3. It has run an algorithm. Mill time as 21, and then blend time as 17.6. Spray rate as 388, and coating viscosity at this level. And then you will get the maximum dissolution of 81.31 with the range or a confidence interval of 77 and 84, which is ranging. This is the optimized factor setting as per the data input. Now that you want to accommodate for the variation also, I said in the beginning, so you go ahead and then run a Monte Carlo simulation. I'll go and then look at the simulator here. I'll click the simulator. Now that you can change any of the distribution here. This is the best part. There are more than 20 options within random function. That's the best part about JMP. You can fix it. I'll change the mill time. I'll make it random here. Look at this. You can change the distribution to normal, weighted, everything. So for the sake of it, I'll make it uniform distribution. I'll change the blend time also to fix uniform distribution. Let me change the spray rate also to uniform distribution. So I'm accommodating the results for the variation in the randomness. Okay, I'll make it random here also and make it instead of normal. I can change anything I want, uniform distribution. So there will be some spaces you would have not tested through your experiment in pharmacy, but you can use this to extrapolate the results or test using simulation. I'll click simulate here. There's one more thing which I forgot to tell you, the noise also. So so factor settings and remember settings, you can always do that. You want to include the variability of the measurement process as well. Use this response noise. Okay, you can add a random noise as well, because not every measurement process will be ideal or else effective. So if you see that your process of measurement is also having issues, you can add a random noise here. So let's keep for simplicity and then say go ahead and simulate for 5,000 runs. Okay, and then okay, it ran. Looks like this is what the result looks like. This is the desirability. And then you can see this dissolution has a rate of 0.016 rate. That's the defect rate. You can see here the value. With the mean of 80, you will get, and the standard deviation of 4. That means even if the mean 80, if you make it a random uniform distribution, this is what the result is. Or else you can change the distribution, make it little more on the normal distribution. You can keep simulating the data. That's the best part about JMP. You can also bootstrap. You want to bootstrap this, go ahead and then bootstrap for some samples, 2005 samples, and then get the data output. So it takes a little more time. You can say 20 seconds. I'll stop them early just for the sake of it. You can see the bootstrap IDs on the dissolution defect rate here. So I can go ahead and then explore it. Or else you want to see the data, you want to simulate the data, go ahead and make a table out of it. You can further explore the simulated data with mill time of this, blended time of this, pre-array. So it gives you a lot of options. But still, you want to find the sweet spot or the most optimal factor setting. There is another profiler called surface profiler. I'll come here and I'll do a little more on the factor profiling called surface profiler. This is a response surface profiler. This is what it goes. And then you can play around with and then optimize your result here. And there's another profiler which I super like, is called contour profiler. So contour profiler gives you the optimal design space. Okay, let me check this way. And let's say I want to have multiple frames here. And I'll take the mill time and then other time on the vertical factor, and I'll go ahead and then show you this. So now this option will give you, what if you start changing? Let me add a little more on the contour grid as well. Okay, the contour grid. So what if I start looking at which is the best dissolution which I can get by playing around the finest spots using the contour profiler? That is something you can also use little more a lens kind of an approach, what you call it as crosshairs, to see, hey, what is that optimal number here? What could be the optimal factor setting? You can go ahead and explore further in detail, because the simulation will give you a result, but as a scientist, you know which are the variables are little more expensive to explore, which are the variables which are easy to control. So you have some basic understanding about the data on the process as well when you do an experiment. So this will give you an option to explore the data in depth by playing around with all these data sets. So this is the best part of JMP. It gives you a little more extra features to play around and find a sweet spot. So look at this. If I take this as 20 mill time of this space, it gives me around 78. So I can optimize it to 79. I can play. And what happens to other variables also? You can see the sweet spot by minimizing this, how the entire contour looks like using contour profiler. So you can do this. Look at that. So these are all visually you can understand where is your optimal factor settings using your design space. Okay. So these are something I thought of showing you this. So for ease of explanation, what I've done is, with due respect to time today, I've chosen a process that has one target variable, that means your dissolution, and 5 influential factors. A similar approach can be applied using JMP for multiple more complex analytical simulation. So the benefit of getting the freedom to further optimize the production process without the need of repeated regression of registration applications clearance clearly exceeds the effort for definition of the design space. So quality by design, when it is, the design space is an important component, and JMP helps you to achieve this very quickly and efficiently, as well as visually also. So I'm just looking at the time here, and due respect to time, I'll save this and I'll show you a little more on the design of experiment. I'll just fit the model. So if I want to see what I did exactly, I'll go here and then click. It gives me all those things, whatever I just did showed you. So you need not save anywhere. Or else you can simply copy paste the output also. So let me run into design of experiment for next 10 minutes. Okay, so next, and then we'll wind it up, and I'll give a little more information on the academic suite, and then we can wind that up session. So design of experiments is an integral part of quality by design for pharmacy. Okay, JMP has a robust DOE platform. If you see as this is DOE, which enables you with not only classical textbook designs like factorial, screening designs, response surface. You can see this classical screening designs, response surface, Taguchi arrays, space filling, mixture design, etc. But also some of the advanced algorithms like designs like super saturated. You can see that special purpose, group orthogonal super saturated designs. JMP also has a special feature called custom design, okay, which accommodates various types of factor. Let me open this, okay. Let me close this also. Close all, yes, okay. So, which accommodates various kind of factors. Um, like constraints, disallowed constraints. You can specify which effects are necessary to estimate and which are desired to estimate given the number of runs. You can also specify number of runs that matches your budget for your experimental situation. So custom designs also support hard to change, easy, very hard to change factors, allowing you to construct split plot or related design. So you throw your constraints, you whatever you want to do, and you have a budget constraints, go ahead and then use the custom design. These are the cutting edge tools which are used in pharmacy industry to manufacture or else find a formulation. So I'll just take a formulation mixture design, for example. Okay, this is how JMP design of experiments is. It has all those classical design, design diagnostics, custom design. I'm building a mixture design here. So one of the example I'll take is the response here is a damping. Okay, damping of the measure of electromagnetic damping of an acrylonitrile powder. So you can decide whether this is, I'll put it as, okay, damping. Okay, damping. You can see my screen. Damping. So I can maximize or minimize whatever it is at this point of time. You can choose, I'll choose none. Let's keep that way. And then I want to add 3 factors, okay, 3 mixture factors. Look at this, I can add continuous factor, discrete, categorical, covariate, mixture. Because I'm doing mixture design, I'll use mixture factors. So it gives me 3. The first one is here, I have 3 mixture ingredients. One is the copper sulfate, okay, CuSO4. It's a mixture, easy to change. I'll put it as 0 to 0.2 to 0.8. Okay, that is my values it can take. And the second component is my sodium thiosulfate. Okay, it is Na2 S2O3. Okay, Na2 S2O3. With that, it is also 0.2 to 0.8. Okay. And then I'll take glycol, okay, and then keep it as 0 to 0.6, okay. And then I also will have a non-interested kind of categorical variables. I'll call it as 3-level non-mixture environment. Factor of interest is wavelength for me. There are 3 levels. Let me keep wavelength here. I know you might be thinking wavelength is a continuous factor. For the sake of it, let's put categorical 3 levels. And this is what I did. So I said continue here. And I can add main effects, interactions, cross. So I will say 2-level interactions. I can choose main effects or remove none. Okay, so it gives me, I can also choose power quadratic or cubic interactions. That may not be relevant in the mixture design. So 2-level interactions only. And then I'll say make a design. So it gives me, look at this. I can also, it says minimum is 12, and then you can say 18. I want to make a design out of it. Looks like it. Let it take its sweet time. Yeah, it takes 10 seconds to make a design. Let's see what it gives. Okay, so it gives me a design. So it gives me it looks like open the facts. And so let me check first what is the design is all about. Okay, so notice the smallest. Let's start with evaluation of design. Okay, so design evaluation, it gives me this one. So design evaluation, let's see, power analysis. I'm not interested in power analysis. let me see, prediction variance profile. This is very important. Profiler is so important for me. So move the slider here, L1 to L2 to L3. Looks like nothing is changing. That means this is of not interest for us. That's what we decided. So one of the sliders, let's take copper sulfate here. If you start moving like this, look at the curvature here. The sliders for other two mixtures adjust to make the mixture ingredient sum to 1, because this is a mixture design. So you can also notice the smallest relative prediction variance occurs near the center here for the mixture factors. That's how it is positioned. The prediction variance profile, if I want to maximize my variance here, so you can see that if I maximize my variance, notice that relative prediction variance over the design space is 0.8 times the error variance for me. That's absolutely fine. So let me also see a fraction of design space plot here. So what it's giving me, or the entire design space, the relative prediction is around 0.8. This is what it gives me, total 0.8. And the minimum relative prediction variance is around 0.32. Look at this. This is where the 0.32 starts. It mostly centered around near the center settings for the mixture factor. So you can see that it is centered. So design diagnostics outline also you can see here. So the design is optimal relative to the D optimality criterion, even though its D efficiency is very low of 3.6 here, because mixture designs are far from orthogonal due to the mixture constraint, and that's what it does. So then typically have very low D efficiencies. The average variance of prediction is around 0.41, you can see, and this is consistent with the fraction of design space plot which we just saw. Okay, so then I want to simulate the response, make a table. I can change the weightage of this, and then it simulates the responses. In your case, you might have to go and do an experiment. Just for the sake of it, I'm simulated the response here, and then I will create a model and run a model out of it. These are all the things you get as an output. So even the prediction profiler. You can go ahead and then optimize, which I showed you just before this. The one thing is mixture profiler. This is what you will be interested in. So now that I told you how to go ahead and optimize and then see that, look at this. This is what your optimal numbers looks like. If I start moving, this is what, because we said that is can only range from 0.2 to 0.8, and then something from 0 to 0.6, the third variable. So with all this, what is the optimal space, or is the optimal design space for me? You can go ahead and simulate all these responses as well. So this is one way. One of these is I can go ahead and show all the designs, and then JMP has this powerful feature where you can not only understand from looking at the statistics and then the numbers, but also visually seeing the design space or whatever is the visualization of data. You can see that the crosshair, what happens here, it can range from 0.3. You can see the dissolution. Probably I have to minimize this. Let me show a little smaller here. Yeah, let me make a little smaller space so that I can see the design space also. Yeah, there you go. Yeah. So I can go ahead and then see optimize. Again, I showed you, take an interaction profiler here. All these profilers are here, or else you can go ahead and see all this row diagnostics being Durbin-Watson test or factor FX screening, save columns. You can predict, for example, prediction formula. You can save it as, and then you can see this is what it is. Prediction formula. I can run the simulation here only, surface plot or ternary plot here. I can see the ternary plot. I'll say prediction formula here. I can run the same thing here as well, or else any of my profilers I can run here in the graphical tool also. So that's also possible. So JMP gives you that power to go ahead into a discovery mode, and then start unearthing the patterns and then make breakthrough discoveries. So you're all faculties. Let me take last 5 minutes. So JMP also comes with lot of teaching demonstration. I thought of showing this to you people. Sample data. If you're teaching any of your regressions, for example, so teaching scripts are available here. So if I'm teaching, for example, interactive teaching models, if I'm teaching Bayes theorem, basic statistics, or regression, I can go ahead and simulate the data, for example. I can show them a little more. say skew to right my population and have 5,000 samples I want to randomly take. Then I want to show an illustration, animate illustration, and then say, go ahead and then draw random samples. So look at this, as I click this button, even though my population is positively skewed, or as in for example, we can also assume it is unknown, I don't know the distribution of the population, but if I randomly take samples from my population and plot the sample distribution of means, it will be normally distribution. This is what assumption we make, and this is what we teach as part of central limit theorem. So if I say something is changing, people might take some time to understand. But if I show them how it is changing using interactive prediction profilers or something like this simulations, students or the researchers can also understand better. So JUMP is not only an advanced statistical discovery tool for researchers, scientists, and as well as industry, but also it has a lot of inbuilt modules which students can leverage, or professors can leverage to teach better also. And that's the part of JUMP academic team we've been doing. Let me close this. So that's what so there are a lot of things as part of this. The add-ins, the textbooks are part of. If you want to learn design of experiments, the add-ins are part of it, the textbook. So design of experiments, Montgomery. So this is something which I thought of showing. The textbook is part of JUMP. That's the best part. You have an example here, chapters are here. You can go ahead and explore. These are all available on the internet. You can go ahead and explore further. So I'll leave you with that thought. I'm looking at beyond. I've already taken 5 more minutes, but